Okay, I'm going to do a set of notes here, or at least information for you about some of the basics of, no, not some of, but a lot of the basics on specifically descriptive statistics. When we met together, I went through five major ideas: populations versus samples, the idea that the population is everybody within, or every subject or object within a given defined set, and a sample is just a portion of that. And ideally, um, we get a good sample that's representative of that, but that's what we're working from. Census taking is when you measure the entire population. Sampling is when you just measure part of it. Parameters is a number or a measurement about the whole population, and a statistic is a number or a measurement about part of it. Observational studies are when we gain information about a sample or a population without introducing anything into that sample or population. So we don't do anything with them, we just collect data about them. An experiment is where you apply some sort of treatment or factor to at least part of the sample or part of the population. In good experimental design, you only apply the treatment to part of the population, the experimental group, and we control that against a control group. And then we got into a discussion of significance, where statistically significant basically means it could have happened by chance, and practically significant for all intents and purposes means that you have the ability to do something practical as a result of the data set that you're given. All right, so one of the things that I would do, or I do, as part of the course that I teach is to actually introduce some of the error pitfalls that people can make in statistics quite early on. Now, in the teaching framework of things, this is where, like, your students that are not particularly mathy may either really get into this or could get freaked out by this, because suddenly this starts feeling like a science or a social studies class and not necessarily a math class, because a lot of times struggling math students want that, like, show me all the steps thing, and you're getting into like critical thinking stuff here. But this is really just about establishing a lot of vocabulary early on so that you can work with it throughout the course. Um, One of the big things that you want to strike is that there's a difference between causation and correlation. Causation means that one action forces another one to happen. Um, this is not the subject matter of statistics. At no point do we actually prove that one thing causes another, statistically speaking. Correlation we can show. And we're going to talk a lot about correlation, especially when we get into like things that have two random variables. So like you take two measurements on a data set, and then you see if these measurements have something to do with each other. That's something we're going to get into later on. This is something that's observable, and you can demonstrate and measure this. So we use R and R squared as the measurement for correlation, and we'll get into that a little bit later. Another pitfall is working with like reported results. David Simon, the Wire guy, has a great quote that, like, one of the rules of police work in Baltimore is that people lie. People lie when they don't have to lie. They lie for whatever reason. There's one statistician said if you want to see how reported results work, just watch two people on a first date and count the number of lies that they tell each other in the first half hour. And it's just phenomenal how bad that is. especially on sensitive subjects like consumption of alcohol or how much do you smoke or how much do you weigh, how much coffee do you drink. These are just awful places where you're going to get bad results if you have people report them out. Um, Loaded questions are pretty common and they happen a lot in things like political polling. Um, and they're hard to avoid. Like, you want to try to ask questions that are stripped down as much as possible. And, like, we get weird things. Like, do you think we should restrict immigration in order to protect American jobs? Well, the stripped down question is do you think we should restrict immigration? Or do you think that immigration has an effect on like unemployment in America? But if you ask these together, you don't really know which question they're answering when you get this. Other less obvious things are like, what does the SAT and ACT actually pick up? I mean, they're purporting to pick up college readiness, but if you look deep enough, you're going to find that they're tracking things possibly like socioeconomic status or some sort of adversity measure or the background of the student. So, though the SAT and ACT are supposed to be a legitimate measure of a person's college readiness, it's probably a loaded reality that needs to be balanced against something that'll get you a control for some of these other things, because the test itself is loaded, because people who have a higher socioeconomic status or educated parents or more educational resources available to them may score higher even though they may be less functionally ready to do collegiate coursework. So that's it's fraught with peril there. The College Board freely acknowledges and that there's issues there. So like they try to do it in an adversity scale a few years back, which created a firestorm on top of that. But it's definitely a place where the whole testing situation is fraught with loaded questions. The order that you ask questions in can be pretty bad. The example that I gave here in the outline is like if you ask the question, should a politician be elected if they fail to disclose a significant illness? And then you ask the question, should you vote for Brandon Scott to be, do you intend to vote for Brandon Scott? And then, you're wondering, did you lead the person to think that Brandon Scott is failing to disclose a significant illness? So you get biased through the question order there. If a segment of the population is missing from the data, like if you have a non-response from a segment of the population, this is a huge pitfall. You have to question that data. Like, let's say if you took a large school and you asked, a question about racism, and you found that only 8% of the African American students actually answered that question, whereas the general response rate was around 78%, then there's something about that question that's causing some disturbance in your data, and you need to attend to that. You probably want to seriously consider throwing that question out. It's really hard to get good questions, and that's like crafting questions is like huge work for statisticians. Hyper precision. Measuring on the small scale, small changes, things like this is really, really hard to do. If somebody comes in with like a hugely precise measurement of a small shift, like if they have like an actual number of the daily shift in the human population or something like that, you got to call that into question. Another common error is confusing percents and decimals. And like, we're math people and this is what we do, but most people like we'll see like 0.25% and think that that's like a quarter. And that's really, really bad. So usually it's best to reserve percentage notation for situations that are between 1 and 100, and otherwise to use decimals. It's a tough trick to teach kids, but in reporting, if you report things with, what do you call it, decimals within percents, it just gets confusing and convoluted. I put in here, in my humble opinion, that this should all be like talked about early on a course in statistics, because issues that are named here, particularly these 7, will come up throughout the class, and that way you have like a starting point for those conversations. All right, so part of the backbone of statistics is data, okay? And we've got quantitative versus qualitative. That's numbers versus traits, right? Quantitative would be, how many forks are in my house. Qualitative would be like, what color is my car? So these are things that can be numerically represented as opposed to descriptively represented. Usually when we're doing quantitative, we take like measures of center is kind of the goal there, mean, median, mode, that kind of stuff. Qualitative, we tend to talk about percentages, the percentage of cars that are blue. And that's how we derive a quantitative value out of a qualitative situation. So just to be aware, is the data quantitative or qualitative? Continuous, so once we get into quantitative, is it continuous or discrete, right? Can we have parts of parts? Centimeters are continuous. Every part of a centimeter can be broken into smaller parts that have meaning. Cats are discrete. You can't have half a cat. You either have a cat or you don't. So knowing whether your data is continuous or discrete is important. Continuous graphs are represented by curves. Discrete graphs are represented by points. So this is something to be aware of. We use different types of charts and graphs to represent continuous and discrete data. We'll get into some of that when we do visual representations. This is a place where kids get like majorly messed up, and this is this whole levels of measurement thing. Statistics uses 4 levels of measurement. I like to say that we use 3.5. The one that's like a half level is the interval level, because it's almost never occurs, but it does matter for things like degrees Celsius and degrees Fahrenheit, because it's different from other things. All right, so the lowest level of measurement is nominal. This is the place where like a number is standing in for a name. So like your social security number is used instead of your name, or a zip code like 21236 is a number that means Nottingham, Maryland, or 21221 is a number that means Essex, Maryland. So again, it's a place of a number standing in for a name. There's nothing better about 21221 than 21222. It's just that they're different places. So that's the nominal level. Ordinal, we give things numbers that make sense in order. So like if you have a class rank or like a race where the runners are coming in first, second, and third place, like first means you came in before second, second means you came in before third, but it tells us nothing about the distance between them, right? So the distance between the first and second place runner doesn't say anything about the distance between the second and the third place runner. So that's the ordinal level of measurement. Interval distances matter. So, but you cannot form ratios. So let's give why this is the case. And this is where kids get stuck. Temperature is usually about the only thing that works here, and it's if it's temperature in degrees Celsius or Fahrenheit. Um, if we went from, let's say, um, 10 degrees to 50 degrees, then being 40 degrees hotter has meaning. So like the distance from 10 to 50 and the distance from 40 to 80 is still a 40-degree increase, and that means the same thing in both places. However, to say that 50 degrees is 5 times hotter than 10 degrees actually doesn't make sense, because that, like, if you, the easiest way to prove that that doesn't make sense is just convert it all to Celsius, and then you get, like, the ratio is not the same. So that's where you get this weird thing. So the distances matter here, but the ratios don't. And that's really because the zero is not an absolute. 0 degrees Celsius is somewhat arbitrarily chosen as the freezing point of water. 0 degrees Fahrenheit is something arbitrarily chosen because it feels cold. And there's not much more you can do with that. But ultimately, that's why the ratios don't make sense, because there's not a clear distance from zero, or a clear distance from some sort of bottom. When you look at things like Kelvin and Rankine, Rankine is the Fahrenheit version of Kelvin. There you have an absolute zero. There is no negative Kelvin and no negative Rankine. So that's actually on the ratio level. That's why scientists work with Kelvin and Rankine. The only scientists that really work with Rankine are people who like build airships and stuff like that. But Kelvin is the general unit for science. And that you can actually get a meaningful ratio out of. Ratios, ratio level is like everything else, like grams, pounds, anything that has a natural zero in like, so the example I'm giving here is grams. 30 grams is more than 10, so it meets the ordinal criteria. 30 grams is 20 grams more than 10, so the distances actually have meaning. So that means intervals have meaning there. And then an object weighing 30 grams is 3 times heavier than something that weighs 10 grams. So that it has something 30 grams has 3 times as much mass as something that has 10 grams, if I'm going to be more scientifically accurate here. But in the end, the idea of the ratio actually has some meaning. So there's your levels of measurement. This is a place where kids get tripped up, particularly on the interval and ratio levels. And no matter how many times that you tell them that really the only thing that tends to be on the interval level is like degrees Fahrenheit and degrees Celsius, they still get them confused. Okay, sampling methods. So we have to get data. Random is nice, but it's not completely the goal. So let's say over here I have a population with, I don't know, let's use purple. There we go. 1, 2, 3, 4, 5. I'm not going to count out loud. 8. So this is my population. My population has 18 people in it, right? Now, if each person in this group has an equal probability of getting into my sample, so let's say I want to take a sample size of 6, right? Each person has an equal probability of being in that sample. So I could pick 6, and each of these has an equal probability of being in that sample of 6. Then I have a random sample. So each individual element has an equal probability of being chosen. Now, here's the problem, is that what I could do then is I could do something like, all right, roll a 6-sided die, and if I get a 1 or a 2, I'm going to start with number 1, and if I get a 2 or a 3, or 3 or 4, I'm going to start with number 2, or 5 or 6, I'm going to start with number 3, and then I'm going to pick every third person in the list. And if I do that, right, so like, let's say I roll my 6-sided die, and I get, I roll a 3, or a 2. Let's say I roll a 3. I roll a 3. Then the first person on my list is going to be 2. I go 1, 2, 3, 5, 1, 2, 3, 8, 1, 2, 3, 11, 1, 2, 3, 14, 1, 2, 3, 17. I now have a sample of 1, 2, 3, 4, 5, 6 people. Every single person in this list had an equal probability of being chosen by this method, so this method is random. Now, the problem here is that not every subset of the same size has an equal probability of being chosen. All right, so I just chose a subset of 6 things. 2, 5, 8, 11, 14, and 17. 8 had a probability of 1 in 3 of being chosen. Okay, likewise, like the set 1, 4, 7, 10, 13, 16 had a 1 in 3 chance of being chosen, and the subset 3, 6, 9, 12, 15, and 18 also had a 1 in 3 chance of being chosen, which literally means that every single number in this list had a 1 in 3 chance of being chosen. However, not every subset of size 6 has an equal probability. These 3 all have a subset, or have a chance of being chosen at 1/3. But let's say the subset 1, 2, 3, 4, 5, 6, that's a subset of 6 items. 8 has a probability of 0 of being chosen by the sampling method. So this is a sampling method that would create a random sample, but does not create what we're going to call a simple random sample. Okay, so I'm going to back like a bunch of this stuff up and get rid of all of it, and just get back to my original 18 numbers and have a subset of 6. And what I want to do here is I want to pick a simple random sample. And essentially, if I put all 18 balls in a box and I pull 6 out, then I would have a simple random sample, because every single number would have an equal probability of being chosen. And every subset of size 6 also has an equal probability of being chosen. So that's how I get what we call a simple random sample, or it's sometimes called SRS. All right, so that's the one we really want to have happen as a simple random sample, except for doing that with a large population is incredibly difficult, so we tend to settle for something that's less than an SRS. Now, a really bad way of doing this is what's called a convenience sample, which is basically I go and I just pick 6 numbers that I want to use, and those are the ones I use. This can be done by, like, going into the cafeteria and sampling like the first 10 people I find, or just asking my friends what their opinion is, or letting people self-select into a set. A bad idea, because usually you don't get a representative sample that way. This sample will almost always be biased, and it is neither random nor a simple random sample. So convenient sampling is a bad idea. Systematic sampling is what I did at the very beginning here. I pick a starting point, and then I pick every so many numbers on a list. It's not a bad way of sampling, and if you randomize the starting point, you will get a random sample, but as we showed, that's not a simple random sample. So if you pick, like, every third person on the list, that's systematic sampling, or every 9th person on the list, or whatever. Stratified sampling is another way of going after this. So what you do is you take your group here, and I'm going to kind of get another color to work with. And I'm going to break my group into subgroups. So I'm going to break it into groups of 3. Let me make them a little bit bigger. Let's do groups of 3. Okay. So it'll be 10 with maybe, let's put 10 with 17 and 18 here. There we go. Okay, so I've got my little subsets here. And then what I want to do is I break my population into groups, and then I take a random sample of each group. So like here, I pick one randomly, I pick one randomly, I pick one randomly, one randomly here, one randomly there, one at random here. And now I have a sample of size 6. And it doesn't have to just be one from each subgroup. It could be like randomly picking 2 or 3. It depends on how big of a population you have and how big your subgroups are. But so you break it into subgroups, and then you take a simple random sample within each subgroup. Okay, so this is usually used to control against some sort of confounding. In this type of situation, each of these subgroups might be like a different group of people. Like you might have a group of, young folks, middle-aged, older, so forth and so on. Could be young men, middle-aged men, older men, young women, middle-aged women, older women, and then you sample within the subgroups. That would be an example of stratified sampling. If the groups are of equal size and the samples of the subgroups are also of equal size, you would get a random sample. It is not simple random, but it would be random. So stratified means you take sum from all. So that's the key words there, sum from all. I'm going to back this up. I'm going to keep my subgroups. And now we're going to go into what's called a cluster sample. Okay, so clustered sampling is what I'm going to do is I'm going to go ahead and I'm going to pick certain subgroups. Okay, so I'm going to choose this one and that one, and now I've randomly chosen 2 subgroups, but then I'm going to sample every single member of the random subgroups. So like, let's say you go to a school and every single kid has to take English. So what you do is if you want to sample that class, you go and you say, okay, I'm going to grab 3 of the 9 English classes at random, and then I'm just going to say every kid in that class. This is an example of cluster sampling. Again, if the subgroups are chosen at random, this could be a random sample, but it's definitely not a simple random sample. So stratified is sum from all. Clustered sampling is you do all from some. Now, none of these methods, other than like something that looks like pulling balls from boxes, will actually get you a simple random sample. We want SRS. It's like the gold standard for everything that we do, but it's very difficult to achieve, and other methods can get us good results, but they're not going to be as useful as SRS. All right, so next thing that's happening here is, one more time, convenience samples are always just a bad idea, right? All right, so let me get into, what do you call it? Let me back this up and just kind of clear that screen out. All right. Observational studies. Okay. So earlier we talked about the difference between an observational study and an experiment. Something to know about observational studies is that there's 3 major types of them. One, you can think of them as like present, past, and future. The first type is what's called a cross-sectional observational study. This is where like you have a population or a sample, usually a sample, and you take a data point on that whole sample all at one time. Okay, so like you give an AP exam. That's like collecting a whole bunch of data on a sample of students all at once. This is a snapshot of that group at a present time. Now that data set's useful because it gives you a cross section of the group, and you're controlling for a lot because you're doing it all at one time. Um, so that's like the present version of an observational study. A retrospective observational study is what you do is you grab a sample of people and then you look at their historical records. You're not looking at their current reality, but you're looking at past data that's been collected on them. So basically, an easy example of this is something like student admission portfolios. So a college receives an admission portfolio on a whole bunch of students, which are basically sets of past data on those students, and then they can do a retrospective study on those students to make a decision as to who is going to get admitted to that college. Our admissions team here does this. This is an examination of their past records, so that's the retrospective idea that's in past. The last thing is a longitudinal or a perspective or cohort study, and this is where like you gather a group of people that you're going to study, and then you do multiple measures over a long period of time. And they don't always have to be the same measure, but you keep measuring the same group over and over again in different ways. So this is the idea is that you form the group, and then in the future you're going to study them. These are usually highly beneficial and highly hard to keep together because it's hard to keep people together for a long period of time. But like an example of something that was done a few years back was I think it was might have been Connecticut, a small county somewhere, took a group of single mothers, and what they did is not only did they provide an opportunity to do college level education for them, like they provided them with tuition and books and all of this, but they also provided childcare for the child so that the mother would have childcare while going to school and all of this. And then over time, what they did is they didn't study the mother. They actually studied the child to see how the giving the mother additional educational resources actually impacted the child. And they took a look at these children as they developed for over like 25 years just to see what type of path their life took out. And that's like a great example of a perspective or observational study. So that's your past, present, and future for observational studies. Vaccine trials is something that's currently in the news. It would be an example of a perspective study. We get a cohort, and then we look at what happens once we give them the vaccine moving forward. The other side of the coin is experiment. So experiment, instead of just observing somebody, we're actually applying a treatment somewhere. You'll see how I use this distinction, objects and subjects. Like if you do an experiment in physics, the thing that you're experimenting on is called an object of the experiment. If you experiment on humans, we call them subjects. That's an important distinction. Subjects have rights, objects don't. So there you go. In experimental design, there's certain things that you want to make sure are in place. You want to make sure that there's randomization. Now, this is another place where students get confused because we just talked a whole lot about sampling techniques, and now we're talking about ways to do experimental design. Elements that go into this are randomization. You want to make sure that the choice of putting somebody in an experimental group as opposed to a control group is randomized. It's not a form of sampling. You once you have the sample, then you make choices as to which group they're going to be in, and that still has to have an element of random. Experiments have to be replicated, and this isn't just having like control experimental groups that are larger than one. This is actually meaning that, like, from beginning to end, from the process of sampling for your experiment on through collecting and recording data at the end, has to be replicated and done multiple times. Because that controls against like outside factors and confounding, and allows you to say that the results that you're getting from this experiment are actually from the application of the treatment and not from something else. Blinding. Okay. So blinding means basically somebody in the experiment doesn't know what's going on. And usually in an experiment, you have three groups. You have subjects. So these are the people who are hanging out in their little experimental group or in their control group. And then you have administrators, and sometimes they're called techs. And these are the little doodads running around in white coats who are doing things to the experimental and the control group. And then you have a principal investigator, who is the person out here who's keeping track of everything and all of this. So one of the first things is that these people should not know which group they're in. Okay, so the experimental people should not know that they're in a group getting the treatment. The control people should not know that they're in the group that's not getting the treatment. Usually at this point we interject some sort of placebo so that they don't know, so it feels like you're being experimented on, but you're receiving a treatment, but in fact you're not. Now, if these people don't know, we call that blinding. Okay. Now, in an ideal world, the techs also don't know which group is which. They are just simply doing what they were told, and they're giving this group the blue pill, and they're giving this group the green pill, but they don't know which pill is actually effective. Okay, or they may actually just be giving blue pills to everybody, but this blue pill has, you know, a number 1144, this one has a number 1133, and they don't know which one's which. So, if the admins and techs also don't know who's who, this is what we call double blinding. Writing is not my strong suit today. Okay, so this person is kind of firewalled from the whole experiment, and they're setting everything up, and they're like the one that's handing the things to the techs, and the techs are the ones handing the things to the people. The techs are making observations of the people and then giving back this person their thing. So if I have a double blind experiment, the only person who knows everything that's going on is the principal investigator, which is the person who's going to write the report at the end. So if we have that structure, we're in a really good place. It's not always easy to do a double blind experiment, but it is one that is fairly useful. Okay. Let's talk about confounding. We want to control confounding in an experiment. All right, so there we go. Confounding is like when a factor gets introduced and you can't tell whether that factor is causing it or something else. Okay, so like we're doing a drug trial and we want to know whether or not the effect that we're getting is a result of the drug or a result of somebody's gender or their age or something like that. So we try to create controls. And usually in order to do that, you need to have like multiple experimental groups and control groups. Okay. So you might have, you might do some sort of breaking things down where you have a control population that has people of different genders, different ages, different ethnicities, that it's a pretty heterogeneous control group, and then have each of the experimental groups be homogeneous, or you could and then you can compare the results versus somebody who's similar in the experimental group. I mean, like, the ideal situation to control confounding is to have twinning. Like, scientists love to work with matched pairs, or identical twins would be like the ideal case. Like, you have each pairing of the identical twin. One is in the experimental group, one is in the control group. That's like about as close to a completely controlled experiment on people that you would get. NASA did something like this with the Kelly brothers. One of them's running for Congress right now. Mark Kelly, he's Gabby Giffords' husband, is running for Congress in Arizona, and he's an astronaut. And his brother Scott Kelly is an identical twin, also an astronaut. And NASA put Scott Kelly up in the International Space Station for like 30 days and had Mark Kelly stay here on Earth. And they put them through the same activities, not 30 days, sorry, 300 days. Had them do the same activities, one in space, one here on Earth. And then when they got back, they checked the two bodies against each other and learned a heck of a lot about long-term effects of being in space by doing an identical twin experiment, which controls a lot of confounding. So there you go. The classic example of confounding and lurking variables is something like there appears to be correlation between drowning and eating ice cream. That in the end, if you do an observational study, you will find that on days where ice cream consumption goes up, so does drowning. And the R factor on that's like really, really high. But the reality of that is that it's just that when the temperature goes up outside, people eat ice cream more often and go swimming more often. So the drowning in the ice cream is confounded by the lurking variable of the temperature. So there you go. So we want to control for that. Usually at the end of a course, I take on some things about ethics because it's usually when they're like done with the year and they just don't want to do math anymore, and it keeps their interest. But this is actually where it would belong. Is if you're talking about experiments on humans, most institutions require you to have go through an IRB process. Ironically, I don't think Garrison Forest actually has an IRB process, but we definitely won't let an experiment happen without like parental signatures and things like that. But most colleges, universities, and school districts have an IRB process for a student experiment to be involved in. IRB basically says it meets certain ethical standards, and there's a group of people who are trained to look at experiments before they're allowed to be put into motion. At a bare minimum, there are either restrictions or prohibitions about experimenting on these protected groups: pregnant women, human fetuses, neonates, newborns, prisoners, big one. Wasn't so much true in the 1970s. Lots of bad prisoner experiments, like in the 50s, 60s, and 70s. You can go and read about them. They're pretty crazy. We don't experiment on children. Again, there was a lot of not so cool experiments done on children in the 40s, 50s, and 60s. But we're a little bit better about that. And individuals with HIV and AIDS are actually federally protected. So we have to be very careful with that particular population. Groups that, protected groups usually have one of the following. They either have an inability to give consent, which is like human fetuses, neonates, children. or they're in a situation where the experiment could have like high risk, low reward. Oftentimes, that's one of the reasons why we like not on pregnant women, not on human fetuses, not on people with HIV/AIDS, or someone who's exceptionally susceptible to coercion. Again, prisoners, children, individuals with HIV/AIDS would all fall into those categories. Types of vulnerability that even have to be considered, even if they're not in a protected group, are people who cannot, that have mental or communication disabilities. And under communication disabilities, language barriers could be considered there. So, like, if you're doing an experiment and all of the instructions are given in English and you have somebody who's not a native English speaker involved in the experiment, they're considered vulnerable. So, you have to be careful about that. To watch groups that are susceptible to coercion. Students, prisoners, soldiers are perfect examples. Do this or you'll receive a punishment kind of thing, or even just the implied sense that if you don't do something, a punishment might happen. People in deference relationships are like you would never have a parent be the principal investigator for their own child. You definitely cannot have spousal relationships involved in an experiment. That's just not going to happen. Bosses experimenting on employees. Not a good situation because there's a deference situation there. So these are groups that you have to like definitely safeguard their vulnerability. People who are medically vulnerable, you don't do a drug trial for someone for whom this is their only viable treatment option. That seems like unfair, but like if you're believing that your life is dependent upon engagement in this trial, then you don't feel free to leave the trial. So that's pretty scary. People who are dependent upon being an experiment for the financial well-being. Yes, you can give college students donuts in order to be in an experiment. That's perfectly legit, fine. You cannot give a person their living wage in order to be part of a drug trial. They have to feel free. You know, like college saying, no, thank you, I don't want to be in this, you can keep your donut, is a lot different from someone who is, you know, currently unemployed, who's like doing a drug trial so that they can feed their family. So that would be a vulnerability you would have to take into account. All right. The last piece that I just want to take on here are some places where error can be introduced into some of the descriptive statistics. Usually, sometimes sampling can just go awry. Either there's a selection bias in the way you've done the sampling, or you've done a voluntary sample, and a huge bias has arisen. So that would be an example where you would have a non-randomization sampling error, where somehow what you did to choose people in that sample created a biased sample. Insufficient randomization can happen. I mean, this is literally you didn't shake up the box enough when you picked out the balls, or there's something wrong with your random number generator, or, you know, some of the balls were blue, so I picked the pretty blue ones. This kind of thing. The slips of paper were folded, and the ones that were folded twice were more likely to be chosen. These would be things that you would get insufficient randomization. Non-sampling errors, and these are things that happen all the time. Techs make mistakes, and data gets entered badly. Computational errors. So, you know, I multiplied when I should have added. Happens. I forgot to take the square root when I was calculating the standard deviation. I used the standard deviation formula for a population when I only had a sample. That kind of thing happens. Biased questions we addressed a little bit earlier, but you know, any question that has a bias in it can lead you to like massively corrupt data. False data given by respondents. People lie about all kinds of things. Um, uh, that's a typical interesting thing to happen. Using good data to form bad conclusions. That's something difficult to tease out, but there could be like everything is completely awesome with the data set, and you can still have somebody look at that data set and go, oh, it's because, they're athletes, when another explanation available could have been that this happened because they were women, as opposed to, so it's just a matter of making sure that you're actually forming conclusions that are from the data, and that is the only logical conclusion and not just one among many. Using the wrong statistical method. Oh my gosh, this happens all the time, where someone will do some sort of regression on data, and it looks like, they're getting an exponential curve when it's logistic. This is how you got like weird reporting when we had H1N1 news teams were doing like all sorts of exponential growth models, and had they been right, we would have like had 100% of everybody ending up with H1N1. And the reality is that there was a ceiling to this, and it was an S curve rather than a big ski slope going upwards. So they used the wrong statistical method to analyze the data. All right, so I know that that's a lot of information. I'm not going to give any exercises to go with this because, my gosh, I'm close to an hour at this point. But this is a lot of the material language that gets used in a statistics course. And it's like, this would be an entire unit in my class, like, of just going through and establishing all of the terminology that goes along with descriptive statistics so that the students are comfortable and conversant with this type of language, because a lot of this language is new to them, and it's really hard for them to keep a lot of it straight. So I'm going to put up my outline to this, and I'm going to put up the video that you just saw. And if you got questions, email me, or bring it with us next time we get together for a synchronous session there in July, and we'll go from there. So I hope this was useful. I hope it didn't feel too much like drinking from a fire hose, but I'm just trying to get you a lot of information in a short period of time here. All right, thank you.